Hello all, my name is Aviraj Bhatia and today I am going to present our paper on early stage design methodology for energy efficiency in buildings using asynchronous distributed task queues framework. The early stage of building design is very important. So you can see here this chart is known as McClemy chart given by HOK. In our traditional design process, energy efficiency related decisions are taken in the later stages of building design that are construction documentation. If we take design decisions in the later stages, then our ability to impact cost and function decreases, and also the cost of design changes increases. The design decisions must be taken in the early stage, that is pre-design and the schematic design. So in the early stages of building design, we have more freedom, so our ability to impact cost and function is much more, and design changes, cost for the design changes are much less. Why in traditional design we take the design decisions in the later stages? Because to take the design decision in the early stage, we have more variables available. The variability is quite high, and as of now there is a limited use of energy simulation in early stages of design. Because use of energy simulation require expertise and to handle the large number of variables, because in the early stage we have more design freedom, so we have more variables combination to simulate, and to handle the large number of simulations it requires expertise. If we run the large number of simulations, we have large data outputs. How to understand that data, how to analyze data, it also requires expertise. We are providing here an approach to solve this problem. There are different stages, like we need to capture design problem, we need to identify design freedom, and we need to communicate our strategies to user. For this, we have this methodology flowchart. In the step 1 of this flowchart, user provide user inputs. In step 2, we generate input files for simulations. In step 3, we perform energy simulation. Then user get ranking of the parameters, and then in this methodology we are using algorithms, the clustering algorithms, to find out the strategies that can provide user with where energy, the solution where energy is minimum, and then we have the visualization techniques, and we can refine the results. So here is the first step where user provide user input values. So there can be many variables. So for such as I have shown in my screen, one of the variables can be the aspect ratio, orientation, overhang, window to wall ratio, and different type of glass. There are more variables, like we have the insulation, wall insulation, roof insulation, whether we have the controls, daylight control, switch on, switch off, whether we have the cool roof, and each variable can have the like each parameter can have the different variables, like aspect ratio can vary from minimum 1 to maximum 5, and we can divide in the granularity, like the 5 from 1, 2, 3, 4, and 5. These 5 values we can have. So once input parameters and variables are defined by user, next step is to generate input files for the simulations. Generally, we can use you can use any energy simulation tool such as Energy Plus or DO. So all these energy simulation tools at the back end, they have text file where all input related parameters are written. So here is the journal sections of these input files are like building, construction related, the schedules, what is the geometry, internal gains, daylight controls, shading controls, and heating, ventilation, and air conditioning system. So if user is selecting their building type as office, so automatically schedules, internal gains, and related parameters by default office can be selected. And user can have the regular type of windows or strip horizontal windows. Once we have input data files to feed an energy simulation and get energy results, we need to now simulate these input data files. And here, because we are dealing in the early stage of design, we have many variables are available and we have large number of simulation to be done. So one of the solutions is to simulate these files, input data files, on cloud. So we can send these input data files on cloud and run it parallelly and correlate the results. In our methodology, we are using asynchronous distributed task queues or optimize the cloud resources, simulate input data files, and send results back. We have simulated data from all input data files. Now user would like to see the histogram, the spread of the solution space. So you can see this chart is a histogram of EPIs, that is energy performance index, kilowatt hour per square meter per annum. So on the y-axis you can see the number of solutions. So for this particular example, you can see EPI, the most solution lies the EPI of 100 kilowatt hour per square meter per annum. In this example, most solutions are lying in the low energy ranges. So after seeing the spread of solution, even still we have a lot of output data that we need to analyze. How to communicate this output data to user? We need to find out the strategies from the output. So because we have the large number of data, we need to use some kind of clustering, artificial intelligence techniques that can provide the strategies easily understandable for humans. So essential criteria for their explanation is that they must be interpretable. There are several AI methods that can generate rules that are humanly describable. Axis-aligned hyperrectangles is one such method that provide interpretable generalization of multi-dimensional data points. Generally, hyperrectangle boundaries can be easily described with simple rules and easily understandable. So, if we use the clustering techniques, we cannot use normal clustering techniques, ordinary clustering techniques here. So, because the restrictions are, we need set of rules, such as if you provide window to wall ratio between, let's say, 10% to 30%, and this glass or this much depth of overhang if you use, then your building is energy efficient. So a priori it is not known how many clusters are in space and need to be discovered. The clusters can overlap here. Some data points may not belong to any cluster. The cluster have to be ranked based on their size. The cluster should be selected above a user given volume threshold. So here threshold is like I want solutions that are 10% above from the minimum energy consumption or 15%. Such solutions to be find out. So here you can see when we apply the axis aligned hyperrectangle clusterings, that is explainable clustering, the solutions are like shown in this slide. So if you have WWR 10%, then you have design freedom to choose any orientation, aspect ratio, window to wall ratio, and overhang. Just fix your window to wall ratio 10%. Your energy consumption of building is your desired range. So let's say now you want to increase. So WWR 10% is very low. and aesthetically if it is not appealing, and a design team wants to go for, let's say, up to 50% window to wall ratio, then what you can do for this particular example here, if you have good glass like solar heat gain coefficient 0.24, so WWR you are increasing, and you are there is one more constraint or restriction you are involving here on the glass type, then you can have your solution in the minimum energy performance range. You can have any orientation, aspect ratio, and overhang. And similarly, we can have the other strategies. So your window to wall ratio is between 10 to 30%. And if you have the large overhang on windows, then you have the design freedom on orientation, aspect ratio, and overhang depth. So in this slide, you can see the visualization techniques by which we can communicate design strategies to user. So this particular slide shows the complete spectrum of all solutions on this parallel axis chart. So all vertical lines are the design variables like orientation, overhang depth, aspect ratio, glass ID, and window to wall ratio. And last vertical line is our results, that is energy performance index. And all horizontal lines are the different ranges. So we want to be our energy in the lowest range. So let's say about near to the 100 kilowatt hour per square per meter per year. You want to be in the lowest energy consumption. So you can see the blue lines are the range. So this chart is interactive chart. So you can see the parallel axis visualization here, where we have shown two strategies. One is low to medium, low WWR and large overhang. Other is low to medium WWR, high performance class. So if you go with first strategy or second strategy, you can have your energy solutions in the minimum energy range. So in conclusion, we have developed a methodology where you can see on the chart, user can provide the input parameters at the user interface. These parameters are supplied to the backend of the system, where we can use any simulation tool and run simulation in parallel. We can correlate simulation results, and we can process simulation results and give the visualization to use this. By using this methodology, user can easily identify the strategies and visualize their solution in the early stage of building design, which less efforts. In order to get good energy performance, you don't have to compromise on aesthetic or form. Still, you can attain design freedom. Thank you.